Now, we come to the extraction of metals from their ores. As we said, that metals are arranged according to the reactivity series from potassium to aluminium. And then we have carbon, and then we have zinc up till copper. Of course, we have hydrogen here, but we don't mind hydrogen now in extraction methods. So whenever we have any metal before carbon in the reactivity series or above carbon in the reactivity series, then this means that these metals are very reactive and that they cannot be extracted using carbon. They will be extracted by electrolysis because they cannot be reduced. Carbon will make reduction to what it's going to extract. It will make reduction. But for potassium, sodium, calcium, magnesium, and aluminium, as they are higher in the reactivity series than carbon, this means that they cannot be extracted by reduction with carbon or carbon monoxide or whatever. They must be extracted by a way that is called the electrolysis method, as we have taken it in chapter 5, the electrolysis. So they cannot be reduced by carbon and they will be extracted by electrolysis. Of course, in the form of molten salts. We will see that potassium, sodium, calcium, and magnesium are found in nature in the form of chlorides. So we melt these chlorides and we make electrolysis as we did before in case of in chapter 5 in electrolysis, whereas aluminium is present in an ore that is called bauxite. We are going to see now what is bauxite. But other metals that come below carbon in the reactivity series like zinc, iron, lead, and copper could be extracted from their ores by reduction with carbon. They will be, as we are going to see, of course, now, they are going to be extracted by reduction with either carbon or carbon monoxide. These metals would be extracted by the reduction with carbon or carbon monoxide. We will see that zinc is found in an ore which is called zinc blende, and iron is present in an ore called hematite, and we are going to extract them by the use of carbon, where carbon would reduce these metal oxides that are present in their ores, and itself will be changed into carbon dioxide. So either we use coke, carbon coke, or we use carbon monoxide, as I told you. Okay. Now, we will see that the metals that are highly reactive will be extracted using electrolysis. And of course, electrolysis is a powerful tool and it's expensive because it needs a lot of energy to take place. So it is a powerful method, and also it's more expensive than extracting metals by using carbon or carbon monoxide. But the metals that lie below carbon in the reactivity series would be extracted by reduction with either carbon coke or with carbon monoxide. We will see that some of the metals like silver and gold, sometimes, not sometimes, but usually they are present as they are. They are present as elements as they are because they are very unreactive. Now we come to the methods of extraction. As we said that the most reactive metals like sodium, like potassium, like magnesium, they are in the form of chlorides and they are going to be extracted by electrolysis. If you remember, we use in electrolysis, we use two electrodes connected to a direct current supply, and we place these two electrodes in the molten salt, for example, sodium chloride. Then the chloride will be attracted towards the anode, where it's going to be discharged, forming the chlorine gas, and the sodium metal will be attracted to the cathode, where it takes electrons and form the sodium metal. We studied this before, of course, so that's why I'm saying it quickly. Now we come to the reduction method with carbon or carbon monoxide. We will see that, for example, we are going to study this reaction in details, the extraction of iron from its ore, which is mainly in the form iron oxide, plus carbon monoxide. We will get iron oxide, sorry, yes, we are going to get iron, and carbon monoxide will be oxidized to carbon dioxide. So the iron oxide will be reduced to iron, and this is liquid. Here, this is L means liquid. It's not the oxidation state of iron. It's iron metal, but in the form of a molten state liquid, and the carbon monoxide will be oxidized to form carbon dioxide. And the same here, in case of lead oxide, if we use carbon, then it will be reduced to lead, and the carbon will be oxidized to carbon monoxide. Okay. Now, let's start with the extraction of aluminium. We said that aluminium is the most abundant metal in the Earth's crust, and it is found in an ore which is called bauxite. Now, what is bauxite? Bauxite is alumina or aluminium oxide, and it is mixed with some impurities like sand. Sand is silicon 4 oxide. This is sand. Silicon 4 oxide is sand, and iron oxide. Of course, impurities means they are found in small amounts. So the main ore of aluminium is the bauxite ore, which is aluminium oxide mixed with some impurities like sand, and which is silicon 4 oxide and iron oxide. Now, these impurities, because iron oxide is present, would result in the bauxite ore having a reddish brown color. And this reddish brown color is due to the presence of the iron plus 3, because as we studied in the acid base chapter, the iron plus 3 has a reddish brown color. And so it will impart a reddish brown color to the bauxite ore. So if we want to remove this iron oxide, we knew that aluminium oxide is amphoteric. Aluminium oxide is amphoteric. We said that amphoteric means that it can react with acids and bases, whereas iron oxide is a basic oxide. So if I want to get rid of this iron oxide, then I will react the bauxite ore that contains aluminium oxide and iron oxide. So we are going to react this mixture present in the ore. We are going to react it with sodium hydroxide. Why do we react it with sodium hydroxide? Since iron oxide is a basic oxide and sodium hydroxide is also a base, then they will not react together. A base will not react with the base like itself. But aluminium oxide is amphoteric. So when we put sodium hydroxide, aluminium oxide will react with the sodium hydroxide and dissolves. So aluminium oxide dissolves by reacting with sodium hydroxide, but the iron oxide will be left as it is in the form of the solid state. So bauxite is a mixture of, or not a mixture, but it's mainly aluminium oxide, but it has impurities of sand, as we said, silicon 4 oxide, and the basic oxide, iron oxide. So at the beginning, we want to get rid of this iron oxide, not to be interfering in our extraction. So we take this iron oxide, or we take this bauxite, and we add sodium hydroxide. Then iron oxide will not react with the sodium hydroxide because both are bases. They will not react together, so the iron oxide will be left in the form of a solid. Whereas aluminium oxide, which is an amphoteric oxide, will react with the base and dissolve, forming the sodium aluminate that we took before. So it dissolved, okay? And in that case, if we make filtration, we can get rid of the iron oxide, which is the impurity present in the bauxite ore. Now, after that, we say that alumina, which is the aluminium oxide, has a very high melting point, which is 2050. We said before that if we want to make electrolysis, we should melt the salt before we do the electricity or the electrolysis, sorry. Before performing electrolysis, we have to use molten salt. This is a simple drawing for electrolysis. Of course, we'll see now how do we extract aluminium. If we have here a salt like aluminium oxide, it should be in the form of a molten salt, liquid, and in that case we have to heat it. We have to heat it in order to melt the aluminium oxide, forming the liquid aluminium oxide. And this melting of aluminium oxide needs a very, very high temperature, which is 2050 degrees Celsius. So in order to melt aluminium oxide, we need this high energy, and this means that we need a lot of energy, and this is very expensive. The more the energy we need, the more expensive it is. So in order to decrease this melting point, or to lower the temperature at which the alumina melts, we are going to add what we call molten cryolite, which is sodium aluminium fluoride. We add cryolite, which is sodium aluminium fluoride. We have to know this. We have to know its formula. And this molten cryolite, when it is added to alumina, it decreases the melting point of alumina from 2050 to only 900 degrees Celsius. So this is the first use of cryolite. Cryolite is used for two purposes. And we have to know these two, because whenever they ask us about cryolite, they say, why do we add cryolite in the extraction of aluminium from its bauxite? Or we have to mention these two reasons, or else we get only one mark. It's always having two marks. So the first reason is that cryolite will lower the melting point of alumina, and thus saves energy, because we said the more we need, the more the melting point, the more energy we need, and of course it will be more expensive. And the second reason is that it increases the conductivity of alumina. It will increase the conductivity of alumina, means that it will let the aluminium ions and the oxide ions move faster in the electrolytic cell. So cryolite has two purposes. It lowers the melting point of alumina, and the second purpose is to increase the conductivity of alumina. Okay. Now, when we make this electrolysis, we will see that we are going to construct this electrolytic cell. We have, of course, a container that has an opening at its lower end, as we see here. And this container is lined up with graphite. Graphite is carbon, of course, carbon cathode. It's lined up with graphite, where graphite will act here. It will be connected to the negative pole of a direct current supply. And so it will be the cathode in this electrolysis. And we are going to place rods of graphite also, but connected to the positive pole of the direct current supply, so as they will act, these rods will act as the anodes. And of course, we are going to place here the molten alumina, which is the bauxite, together with the cryolite, and they dissolve at 950 degrees Celsius together. Okay, now we have here in this container, we have, we said, aluminium oxide in the molten state, and this means that we have aluminium ions and we have oxide ions. So in that case, at the anode, what will happen at the anode? The anode is the plate or the rods that are connected to the positive pole of the direct current supply. So this means that the oxide ions are going to be attracted, because they are negatively charged. They are the ones to be attracted to the positive anode. And there, every 4 oxide ions will form oxygen, 2 oxygen gas plus 4 electrons. or else we can write two oxide ions. We can write here two oxide ions. Two oxide ions will form O2, and then every oxygen will release two electrons, so both will release four electrons. Okay, this is the reaction happening. This is the half ionic equation happening at the anode, and at the cathode we will find that aluminium ions will be attracted towards the cathode, where they are going to get the electrons that comes from the anode to form the aluminium metal. Okay, so if we want to add up these two equations, then we said before that the number of electrons that comes out at the anode should be equal to the number of electrons that are needed to perform the reaction at the cathode. That's why we have to multiply the first equation by 3 and the second equation by 4 to get the whole or the overall total reaction, where we will see that 6 oxide ions would react with 6 oxide ions will react with 4 aluminium ions to form 3 oxygen gas plus 4 aluminium metal. Of course, it's in the liquid state, molten state, and we don't have any electrons. They are canceled. And so we get molten aluminium right up here from this opening at the lower bottom. Okay? Understand, or shall I repeat anything?
I understand.
Okay. Now, if we look here, we have also cryolite, and cryolite is sodium aluminium fluoride. Okay, so we have fluoride ions as well. So as a second product in this reaction, the fluoride ion is also attracted towards the anode, where it will form fluorine gas. And we know that all halogen gases are toxic gases. That's why this reaction should be done in a fuming cupboard. But now we said that at the anode, oxygen gas comes out. As you see, these are bubbles of oxygen gas. So as oxygen gas is coming out here from in between the positive electrodes, we will find that the positive electrodes are made up of graphite carbon, so it will react with oxygen, forming carbon dioxide gas. So as oxygen is released from the electrolytic cell, it will react with the material of the positive anodes in this electrolytic cell, which are made of graphite carbon. So the carbon would react with oxygen, forming carbon dioxide. Okay, so of course, by time, the positive electrodes will be depleted. It means that they have to be changed every now and then, because they react with the incoming oxygen, forming carbon dioxide. So by time they have to be replaced. We have to replace them. So these are the reactions that are taking place at the anode. 6 oxide ions would give 3 oxygen molecules plus 12 electrons. And at the anode, at the cathode, aluminium ions would react with electrons to form the aluminium metal. And also at the anode, the oxygen gas that is produced here will react with carbon electrodes to form carbon dioxide. So the carbon blocks will be eaten away and need to be replaced. So the overall reaction is that the aluminium oxide that is present in the bauxite ore will change to aluminium liquid and oxygen gas. Okay, and as I told you, fluorine gas evolves as well at the anode. So the products at the anode will be 2 oxide ions minus 4 electrons gives oxygen gas. The carbon plus oxygen will form carbon dioxide gas, or carbon plus less amount of oxygen, as we say in an insufficient amount of oxygen would produce carbon monoxide gas. And also the fluoride ions would be oxidized to form the fluorine gas by losing electrons. Now, there are some properties of the aluminium that we extract in this, of course, by this method, or these are the properties of aluminium in general, that they have a bluish silver shiny metal. It's a bluish silver shiny metal. It has low density. Low means light. Its iron is 3 times heavier than aluminium. It's a good conductor of heat and electricity. It is malleable and ductile because it's a metal, so it has the properties of metals. But it has a very important property, that it resists corrosion. When aluminium is subjected to oxygen, it will form an oxide layer that will prevent the inside of the aluminium to be itself oxidized. So only it will be oxidized at the surface, because the oxide layer will form a layer on the aluminium, and it will prevent further oxidation of the aluminium metal from inside. It is it is not a very strong metal, but it can be made stronger by forming alloys, by adding it to other metals to form the alloys. And it is non-toxic if it is present in certain amounts, but if it's taken by people in large amounts, then this would harm them. As you see here, that aluminium is very important. It has a very important use. It is used in making overhead cables. You see, these are overhead cables that you see whenever you are traveling from a place to another place. We see these pylons, and these wires that are connecting one pylon to the other from one city to another. These wires are made of aluminium, because aluminium is less dense than copper. We usually use copper as wires, especially in homes or in workplaces or whatever. We use copper to conduct electricity. We use copper wires, but in streets we use aluminium wires instead of copper, because it's less dense than copper. And as it is less dense than copper, then we will not be in need to put many pylons. We have to only add only a fewer number of pylons. If we use copper instead, we will need a lot of pylons, more than that, because copper is heavy, it's dense. And also aluminium is a good conductor of electricity. It is malleable and ductile, so we can use it in overhead cables. But in order to strengthen the aluminium, then a steel core is placed in the middle, and then surrounded by aluminium. Okay.
Um,
Do you have any question concerning the extraction of aluminium?